Everyone says solid-state batteries don't exist yet. They're wrong. One is flying over a Chinese city right now, packing double the energy density of a Tesla, and no one in the EV world is talking about it. For years, the narrative around solid-state batteries followed a familiar script. Laboratories publish breakthroughs. Automakers announce timelines. Timelines get pushed back. The public grows skeptical, and the technology quietly remains out of reach. At least, that's what most people believe. But something shifted in China, quietly, without much fanfare in Western automotive media. In Guangzhou, the same city where GAC builds the Ion brand and XPeng operates its headquarters, a parallel industry has been growing at a pace that feels almost surreal. Walking through certain districts of the city, you encounter something unexpected. Storefront after storefront dedicated to electric flying vehicles. Not concept models, not renders. Actual aircraft displayed for the public, built by companies actively competing for the same slice of sky. 20 different manufacturers, one city, all racing to build what China officially calls eVTOLs, electric vertical takeoff and landing aircraft. The term hasn't quite caught on globally. Flying cars feels closer to the truth, even if the engineering is closer to a drone scaled up to carry human passengers. This is where solid-state batteries made their real-world debut. Not in a luxury sedan, not in a performance SUV. In an autonomous flying vehicle operating commercial routes above Chinese cities. The question is, what does that mean for the cars we drive on the ground? To understand why this matters, you need to understand the core limitation that has defined battery technology for the past 30 years. Conventional lithium-ion cells, the kind inside a Tesla, a BYD, or virtually any EV sold today, use a liquid electrolyte. That liquid is what allows lithium ions to move between the anode and cathode during charging and discharging. It works. It works well enough that the EV industry has scaled to millions of vehicles per year on the back of it. But liquid electrolytes carry an inherent ceiling. Energy density tops out around 250 to 300 watt-hours per kilogram for the most advanced commercial cells available today. Push beyond that, and thermal management becomes a serious problem. The chemistry becomes unstable. The risk of what engineers call thermal runaway, in plain language, the battery catching fire, increases significantly. This is why range anxiety still exists. It's not that engineers haven't tried to build bigger batteries. It's that beyond a certain point, making a battery larger and heavier stops being a solution and starts becoming a new problem. You're adding mass to solve a range problem, but mass itself reduces efficiency. It's a diminishing return baked into the physics of the system. Aviation makes this problem even sharper. In a car, you can tolerate a heavy battery pack distributed across a flat floor. In an aircraft, every additional kilogram is a direct cost to lift, to energy consumption, and ultimately to how far the vehicle can fly. The weight-to-energy ratio isn't just an efficiency metric in aviation, it's a safety constraint. This is precisely why the aerospace sector, not the automotive sector, became the first real-world proving ground for solid-state technology. The incentive to solve the energy density problem was simply higher. A flying vehicle with poor range doesn't just disappoint its owner, it creates a serious operational and safety limitation that no amount of software optimization can fix. The pressure to find a better battery was not a commercial preference in aviation. It was an engineering necessity. This is where EHang and Shenzhen-based Inks Energy enter the story. The two companies jointly developed a lithium-metal solid-state battery built around a metallic lithium anode and an oxide ceramic electrolyte. The electrolyte, the component that replaces the liquid in conventional cells, is a dense ceramic material. It doesn't leak, it doesn't degrade the same way, and critically, it enables a fundamentally different anode chemistry. The result, 450 watt-hours per kilogram. To put that number in context, the most energy-dense cylindrical cells Tesla uses in its vehicles deliver roughly 260 to 280 watt-hours per kilogram. The solid-state cell developed for aviation delivers nearly double that figure. Not in a research paper, not in a controlled laboratory environment. In a certified commercially operating aircraft, the AH-216S, EHang's flagship autonomous passenger aircraft, flew for 48 continuous minutes using this battery. When compared directly against the NMC lithium-ion cells the same aircraft previously used, travel distance improved by 60 to 90%. The range of that variance is straightforward to explain. Wind conditions, altitude, and payload all affect energy consumption in the air far more dramatically than they do on a road. A headwind costs range, a tailwind gives it back. The 60 to 90% figure reflects real operational conditions, not a single optimized test run. What makes the oxide ceramic electrolyte significant beyond raw energy density is what it eliminates. There is no liquid to leak, no volatile chemistry to manage under extreme temperature swings. The structural integrity of the cell is higher, which matters enormously in a vehicle that experiences vibration, pressure changes, and the kind of mechanical stress that comes with vertical takeoff and landing cycles. The battery is not yet available as a standalone commercial product. It comes integrated into the aircraft. But that distinction matters less than the underlying reality. This chemistry is working. It is operating in a certified vehicle. It is carrying passengers. The development stage is over. Now consider what this chemistry does if applied to a ground vehicle. A modern AV with an 80 kilowatt battery and a real-world range of around 600 to 700 kilometers. Already a strong performer by current standards, running on cells with double the energy density. Conservative projections suggest range figures approaching 1,200 kilometers under standard testing conditions. That is not a speculative number. It is an extrapolation from a chemistry that is already flying above Guangzhou. The competitive implications of this development are difficult to overstate, and they cut in an unexpected direction. Toyota has spent more than a decade positioning itself as the company that would deliver solid-state batteries to the mass market. The company's communication around this technology has been consistent and confident. By 2027, by 2028, by the end of the decade, the timeline has shifted repeatedly, but the promise has remained. Toyota's credibility, to a significant degree, is now tied to being first. But EHang and Inc.'s energy didn't wait for the automotive supply chain to be ready. They built for aviation, where the performance requirements were urgent and the regulatory pathway, while complex, did not require the same volume manufacturing scale that automotive production demands. They solved a harder problem, higher energy density, in a weight-critical application, and they did it commercially. Meanwhile, in Chengdu, a 6-seat electric aircraft is undergoing certification testing with a range of 200 kilometers and a cruising speed of 230 kilometers per hour. In Guangzhou, a lift and cruise hybrid design, combining vertical rotors for takeoff with a rear pusher propeller for forward flight, is being tested for cross-city and coastal routes. China's government has committed to a 15-year subsidy strategy to develop what it calls the low-altitude economy into a structural pillar industry. The aviation sector is not a detour from the battery revolution. It is the leading edge of it. The vehicles capable of clearing 200 kilometers in the air, powered by cells at 480 watt-hours per kilogram, are the proof of concept for the ground vehicles that follow. The combustion engine did not die because of a single announcement. It began to lose its inevitability when the alternative became undeniably real. We have been waiting for solid-state batteries to arrive in our driveways. We imagined they would come from a press conference, from a product launch, from a polished reveal on a stage somewhere. They came instead from the sky above Guangzhou, from an autonomous aircraft that carries passengers on sightseeing routes, silently, without a pilot, running on chemistry that the automotive world has spent a decade promising and hasn't yet delivered. The technology is real. The energy density is real. The 60 to 90% range improvement is real, measured not in a lab, but in actual flight hours above an actual city. The only question that remains is how long it takes for what already flies to find its way to the road. And given everything we've just seen, that wait may be shorter than anyone expected.